All right. So this picture is from a game I think we've all played. What is it from?
Space Invaders.
Space
Call of
Invaders.
Duty.
Call of Duty. Okay. This picture is a screenshot from
Space Invaders.
From
Angry Birds.
Angry Birds. Okay, good. Now the picture. The reason why I like bringing up Angry Birds is because it is a great example of projectile motion, which is what we're working on. Okay, Unit 4, Section 6.1. The reason why I have this picture on here is because you guys all have experience playing this game. Okay, you guys know how this game works. When you grab the bird and you pull it back completely straight back this way, completely in the X direction, where does the bird go?
Backwards.
Straight in the Y, right? If you pull straight down in the Y direction, where does it go? Upward, right? Because it's like a slingshot. You pull back in a certain direction, and the bird gets launched in a direction completely opposite to that direction, right?
Yep.
My 2-year-old daughter doesn't quite get it. She wants the bird to go over there, so she does this. Doesn't work. Makes me laugh, though. Then when she gets it right, she gets happy.
Why don't you teach her some physics?
I try to. She just says, no, and that takes the iPad away. Okay. All right. So, or she goes, in mine, and takes it away. It's fun. Maybe she should record sometime. But, here we go. Angry Birds. No, she just knows that I hog the iPad. So, iPad. Whatever it is, the thing. The thing that Apple makes that's fun that holds Angry Birds in it. All right. So the birds live inside. You know what I'm talking about. All right. So, yeah, they do. Mine do. Stop ruining my fantasy here. Okay. All right, back to Angry Birds. I want you guys to draw the velocity vector and the acceleration vector at each of these locations. Now, if you're taking notes, I try to get a picture of Angry Birds to go on the back of your note page, but it would have wasted a ton of ink and you won't be able to see half of it. All right? So, if you want to just draw a quick sketch of this, that's fine. You do not need the building. You do not need the slingshot. You just really need this red shape. What's this red shape maybe called? A parabola, right? And that red line is the what for the object? Nope.
Oh, the trajectory.
Trajectory, nice job. It took first hour like a half an hour to figure that out.
I gave you the
That's what you got Kyle in class.
and you just added the rest, so it was 50-50.
Okay. So that red path is the trajectory. There's also a burgundy path.
We put it on the back.
You can draw where you want because you're going. This is actually for an example.
Wait, can we have more circles?
Yeah. You shouldn't have more examples than me.
No, more circles.
You shouldn't have more.
Well, I messed up.
Only 7 circles, 0 to 6.
I have 8. Oh wait, I skipped a number.
It's a wonder you're in this class. Can't count.
I went 5, 7, 8.
Okay.
But I still have 7. So
All right, guys. Drawing picture does not mean top. Okay.
But I need more time to draw.
I don't know how to draw the vectors. Not you gonna teach us?
Well, think about it, Kyle. In Angry Birds world, is there air resistance?
No.
No. So what's the only force acting on the Angry Bird when I shoot the red bird and it follows this path right here? What's the only force acting on it? Gravity, right? Which way does gravity point, Jameer? Down. So there's only one force acting on that points down. Which way is it accelerating?
I mean down.
Down, good. Because Newton's second law, which has an effect on this problem. Newton's second law, F net equals ma, says the net force is in the same direction as the net force is in the same direction as the acceleration. Perfect. So if only gravity is acting on the bird and gravity pulls down, then which way is the acceleration? Down. What?
Okay.
I'm trying to shoot it over my back with this. Oh, I caught it that time. It's the first time I did that. Show fifth hour of that.
Is it
girl?
being
Second
recorded?
time. 2 in a row, yeah.
Wow.
Stupid human tricks. All right. So, 0, 1, 2, 3, 4, 5, 6.
7.
No, we started at 0, so there's 7 dots. We started at 0. Right? So, this is time 0 where we started. What's the direction of acceleration? Kyle, take your seat. Stop working on projectile motion with that piece of paper. All right? So, 0 through 6. Where's the acceleration? Anybody know?
Downward.
Downward. Because the only force acting is
Gravity.
gravity.
Wait, but you're gonna make it.
Now, what happens to this acceleration vector as we go through the trajectory, as Katrina and Kyle called it? Remember, trajectory is the path of the projectile, right? The projectile is the red Angry Bird, which I've shot at 2 different angles, and we'll talk about that in a second. Okay. But what happens to the acceleration? Kind of a trick question. What happens to the acceleration? Nothing, right? The acceleration is the same the whole way. Just like on Earth, what's acceleration due to gravity? Good, 9.8 meters per second squared. So Whitney's phone just dropped at 9.8 meters per second squared.
Actually, it hit a bunch of stuff.
Good.
Yeah,
So-
some errors.
All of these vectors should be the same
Length.
Why did
length.
this one?
Jameer. Okay. Good way to get ISS, but you're just going to shout out random things.
Well, I do that.
Well, yours are kind of relevant sometimes. Okay. So those acceleration vectors should all be the same length. I don't think they are.
It's okay, Rex. We understand.
4 is way too long.
There you go. All right. Does that make sense, guys? Because the whole way this object, this Angry Bird, is experiencing the same
Acceleration.
acceleration. Okay. Now velocity vectors. Okay. Am I looking for average velocity or instantaneous velocity? Instantaneous. The velocity at these specific instants in time, right? Okay.
Oh, we actually learned.
Think about it this way. If we turned off gravity, so this was Angry Bird's face, right? And I shot 0 in this direction, what's going to happen to it?
It's just going to keep going that way.
It's going to keep going. So what's its instantaneous velocity right here? Is it horizontal, vertical,
Line
or is it somewhere in the middle?
in the middle.
Somewhere in the middle, right? What on this picture gives me the indication of that direction, that velocity?
The red one.
The red line, the trajectory. Remember that whole tangent to the line stuff we were working on earlier? Right? The instantaneous velocity is tangent to the trajectory at that point. Now, some guys thinking tangent. We're not doing opposite over, Jason. No, tangent means parallel to the line at that point. All right? So we could say, we could make a note, Kyle, because you said you didn't know how to draw the velocities, right? We could say that the instantaneous, and this goes on your notes from Friday or Thursday, instantaneous velocity of a projectile is parallel, which means in the same direction, to the trajectory. Okay. So the instantaneous velocity of a projectile is parallel to the trajectory. Okay. At that spot.
In that moment of time.
In that moment of time. So, number 1. Where's number 1 going to point?
A little that way.
Okay, so it's going to turn which way? So it's not going like this, it's now going to be going downward, right? What's going to happen to the length of that vector?
It's going to be the same.
Rex says it's going to be the same.
I think it's gonna get bigger.
Kyle says it's going to get bigger. Omar says it's going to increase, get bigger. It's not a trick question. Let's think about components real quick. You guys know about components of vectors, right? You guys did a whole worksheet on Friday about components of vectors.
Sure,
Okay? If I draw a green vector right here as the x component, something like that, right?
Yeah, but
Would you guys agree that's the x component of velocity?
just
Which way does the y component point? Up. Right? So this could be the y component, right?
no, it can't. It's
Would that be the y component?
Yeah.
Does that make sense?
Sure.
Now, this acceleration is going to affect one of those vectors, the blue one or the green one. Which one does the acceleration affect? The blue one. What does the acceleration do to that blue vector? decreases it. Okay? This acceleration is going to make this blue vector longer or shorter? Shorter. Okay? If you don't believe me, take something in your hand and throw it up in the air. Right? As the object goes up, what happens to its velocity? It decreases because of gravity. Until it reaches its highest point, where velocity is 0. Okay. So as we go up from 0 to 1, what's going to happen? What's going to happen to the velocity vector? It's going to get longer or shorter? Shorter. And it's going to decrease. It's going to get shorter, and it's going to turn.
Up.
No, it's actually turning down. Yeah.
For what?
Because acceleration is. I did not get that. So at 2, what's going to happen?
It's even smaller and turn even more.
Going to be even smaller and turn more. That's terrible.
We just expect it.
You just expect at this point. Okay. So Kyle, you got the idea now? No? Okay.
Still playing. That's something. Can you explain this to me again?
No, you
I
should
was
pay
listening,
attention.
I got it.
Okay. So Kyle, at each point, the velocity vector is starting to turn because the object accelerated downward, right? So that's causing the velocity to change direction. The reason why it causes the velocity to change direction is this acceleration is making this blue vector, which is the x or y component. X or y the y component. It's making that y component longer or shorter.
Start over again.
Okay. This blue vector is the x or y component.
Yep, I know. It's a Y.
Why? This acceleration is what's the blue vector? Makes it longer or shorter? Remember, acceleration is the change in velocity, right?
Yep.
So the acceleration makes the blue vector longer or shorter? Saying the velocity is changing, instead of going up, the velocity is changing by making it go down, right? Okay, real world example. I throw the marker up in the air. What happens to its vertical velocity as it goes up? Watch, ready? What happens to the vertical velocity as it goes up higher?
You got it, Kyle. 50%, you have a 50-50 chance.
Yeah, 50-50 chance. Either increases or decreases, right? What happens?
It increases.
It does not increase. What happens to it? What happens to it?
I don't want to.
Okay, it decreases, right? Because the acceleration is downward, that means it changes this vector by making it shorter because the change in velocity is down.
Don't touch me.
Okay? So the acceleration makes the blue vector shorter each second. Okay, by 9.8 meters per second squared. Right now, these points are not 1 second apart. They're less than a second. Okay? So the blue vector will be a little bit shorter after each one. So since the blue vector is a little bit shorter, it's taking the opposite side of my triangle and it's making it less, right? Since the opposite side of my triangle is making less, that means my hypotenuse gets shorter, right, which is the black line, and the angle gets less. Okay, does that make sense?
Mm-hmm.
So that's why our velocity is gradually getting smaller and turning. Okay? Rex,
When it starts to go down, does that mean it's going to get bigger?
what do you think? What's the acceleration going to do to the blue velocity when we're going downward? It's going to increase it. Okay? So I want you guys to add 3, 4, 5, and 6 if you haven't done so already.
Don't touch me.
Okay? Could also use your knowledge of Angry Birds for this one too. Okay? When you're launching the Angry Bird, okay, it seems to come out with a really big initial velocity, right? That initial velocity slows down until we get to the highest point, and then what does it do? Goes down, but it starts to increase, right? Let's do the yellow bird, then it
So
increases when you
between
catch
3
it.
and 4 it increases?
Yep.
No.
Yep.
Mine is different, so it's
As long as 3 is at the highest point, Katrina.
no 4 is at the highest point.
Okay, that's fine. So then yours will actually get smaller between 3 and 4 then.
But it hits the thing, so it stops.
All right, so at 3. I said ignore the building earlier, didn't I? Okay. At 3, which way is the velocity? Horizontal, because it's parallel to the trajectory, right? At 3, the trajectory is completely horizontal. Okay? And that's not completely horizontal. Here's that one. Got it.
It's
Okay.
too long.
Too long. So the first one probably would have worked. Okay. At 4, what happens now?
It gets larger.
Okay, it gets larger and points downward. Good.
Good.
5,
Same thing. Repeat.
6.
Large.
And completely
Yeah.
I know. I probably
For
could.
number 2,
Play a lot of Angry Birds. Have your reps.
Me? No.
Okay.
Yeah,
The best comeback ever. Yeah, huh? Okay. So those vectors make sense, guys.
They sure do.
Thank you. All right. Yes, Cal.
for number 2 to 3, is that one supposed to be pointed up like that?
2?
Yeah.
Yeah. I mean, 2 might be a little long. It could shorten a little bit, but.
But it's like going upwards. It's supposed to be in line, or is it?
Well, vectors are straight; they're not parallel to line. This vector does this trajectory doesn't curve a lot between 0 and 1, right? Between 2 and 3, it curves a lot more. Do you see that curve? Okay, that's because the acceleration is a bigger portion of the velocity, so it causes it to turn a little quicker. Okay, does that make sense? So the reason why it looks like that is because the line is turning more at that point. Okay. All right. Now, do you guys remember components of vectors? Components of vectors. We did that on Friday and Thursday and Wednesday.
Yeah, I know.
We didn't do that on
Maybe not Wednesday. On Friday and Thursday, right? Components of vectors. We have the x and the y component. Right, Kevin? It's the part of the velocity that goes in the x direction and the part of the velocity that goes in the y direction, right? Right? So here I have 2 paths right here, right? I have the red trajectory and the burgundy trajectory. Those are 2 different shots in this round. Okay? Now, what can you tell me about the x components and y components in the 2 paths? Which one has the bigger x component? The burgundy one or the red one? The burgundy one, right? Which one has the bigger y component? The red one, right? Because remember, larger angles means we have more y. Okay, the red one shot at a larger angle. Does that make sense, guys?
Yeah.
Okay. Now, that analysis of the components, the x and y components, I want you guys to use that to break these black velocities, okay, black velocity vectors, into the x and the y components. Okay? So, it's kind of like what I did here, except for I don't want you to draw that blue vector right here because that's not in the right spot. Okay? That's a vector addition problem, isn't it? Right? Where do you think I want you to draw that blue vector?
You don't.
I want you to draw it right there. Darn.
Damn that bridge.
Oh, yeah. You don't. Rivers. I want you to put those in. Okay? So you guys see what I want you to do?
No.
Okay. So I want you guys to draw this blue vector, which is the x or y component, the y, and this green vector, which is the x. So I want you to draw those vectors at positions 1, 2, 3, 4, 5, and 6. Can you guys do that?
Yeah, sure the blue does get smaller, right?
I don't know. Think about it, Skylar.
Oh.
Yo.
my brain was
Eric, Jameer, I've asked you to do something. Okay? Yeah? So I come back and look at it, start done? Surprising, you're hiding your face. So I want you to draw the x and y components of the velocity.
It keeps getting smaller.
Or you can do it in paper, that's fine. Sorry.
How cute.
Have you guys seen that line where the guy's like, hey, black people always black people during a fire drill, so the fire alarm went away. And the guy would answer to like the fire drill sound.
Oh, the George.
Monty, are you done?
Oh, almost.
Okay.
I think the first one.
All right, guys.
What up?
Oh, I'm not gonna worry yet. While you are drawing these up, or once you're done, if you finish early, I want you to start thinking about the velocities. Okay, which point has the largest velocity in magnitude, and then start thinking about the components too. Which point has the largest x velocity? Which point has the largest y velocity? Okay, and do the same thing for the smallest. Which point has the smallest overall velocity? Which one has the smallest x? Which one has the smallest y? Okay. I want you to be thinking about that as you're drawing them or after you're done drawing the components. Okay. Or if you're waiting because you don't want to make a mistake, then actually not using this. We're going to use this one for example
Wait, George.
All right, about 2 or 3 more seconds. Cal, you need some help? Okay. What's going to happen to the x velocity? The green vector. Let's get into the green vector.
For which one?
For all of them. No, for those. 0, 1, 2, 3, 4, 5. What's going to happen to the x velocity?
My
upgrade's not so
So what's going to be the x velocity? It's going to stay the same. What's going to be the y velocity?
Mom, what did you tell me?
Nicknames for everyone.
It's going to get, after 3 it gets bigger, right? But before 3 it gets smaller, then it gets bigger.
Well, no, like 3 weeks or so.
Why do you have 2 copies now?
I think I had ready.
Oh, well give me the extra.
George, no.
It'll work out, trust me, George.
Okay.
When we get to the example, if you want to switch, you can. Okay, but trust me, I think you'll be all right. Maybe you'll be ahead of us in the example. Okay.
You're so cool.
All right. Green vectors x. Okay. Blue vector is y, right? So that's vy and vx. Kyle.
Somebody told me to ask him a question.
No, don't ask him a question because then I have to explain things again because you're focused on George. Okay. So, which way? Or what happens to the green vector as we go?
Does stuff.
Stays the same.
Stays the same. Why does it stay the same, Kyle?
Because you told me.
Michael, why does it stay the same? And that's how you came to the conclusion. Michael, why does it stay the same?
Because it's not going any further distance. I don't know.
It's
Oh, there's
going
no acceleration.
consistently.
There's no acceleration, right? In the x direction, there's no acceleration. This acceleration is only in the
Why?
y. So the x velocity at 0 is the same at which point?
6.
6. The x velocity we start out with is the same the whole way through. Okay? So all these green vectors, oh, don't right there. All the green vectors should be the same length as this vector right there. Okay? So if that's not the case, maybe we want to fix your picture. Okay? All your green vectors, all your x components of the velocities should be the same length. If you look, mine are all pretty close. Okay. Now, the green vector and the black vector, they are 2/3 of a triangle, right? The green vector and black vector are 2/3 of a triangle, correct? What's the other third of the triangle? The y component, right? The y component of these triangles, the third leg that we are missing, right? That is our y velocity, our vertical velocity. Okay? So at this point, our vertical velocity is this length. That's the vertical velocity. Vertical velocity. What's vertical velocity here? 0, right? So all these have been up. Now my vertical velocity is down. Does that make sense, guys?
No, it doesn't.
What does make sense, Rex?
I'm 5. Vertical velocity is kind of the same.
Oh, it shouldn't be slanted.
I thought that was supposed to be.
That's me just working too fast. Better? Right? Does that make sense, guys?
Yeah.
Yeah. Are there any questions? Eric. Okay. The black line is the overall velocity, instantaneous velocity. Okay. The instantaneous velocity is parallel to the trajectory at that spot. Okay. So the black line is like the hypotenuse for the triangle made by the x velocity and the y velocity. Okay, does that make sense? So at 3, we have no vertical velocity because these two velocities are both pointing horizontal. Are you talking about this one? Talking about the downward A? Okay, that's the acceleration vector. That's because of what force? What force? What force pulls down? Gravity, right? Gravity is the same in all these locations. It only pulls down. And that only changes the blue vectors because they're both vertical. It does not affect the green vectors. Okay? That's what that demo we did on Friday comes in, on Thursday comes in. Where we shot the ball and dropped the ball. Okay. All right. Here. Green and black are exactly the same length, pointing exactly the same direction, right? So what does that tell me about the vertical velocity? 0. So at point 3, vertical velocity is 0. You want to definitely make note of that. Okay? Katrina, that's why I said make sure point 3 is your highest point, right? But you said point 4 is your highest point, right?
Yeah.
So whichever one's your highest point, because I know not all your pictures might look exactly like mine, whichever one is your highest point, your vertical velocity must be 0. Now, I asked you guys to consider magnitudes of velocities, right? Right? Okay. 4 velocities. So just for velocity, just for the combined velocity, the black velocity vectors. Okay. The black velocity vectors, which one has the largest magnitude?
I would say number 0 and 6.
Okay, 0 and 6 are tied. Okay. And Rex, you would be correct. Okay.
Woo!
4 velocities.
Nice
The
job.
magnitude, which means just the length. Okay, we're not worried about direction. Okay. The velocity at 0 and the velocity at 6 are equal.
So,
Right?
velocity 1 and velocity 5 are equal.
Okay, good. Are they greater than or less than 0 and 6?
Less than.
Less than. Okay. V1 is equal to V5.
And V2 is equal to V4.
V2 is equal to V4. And
V3.
V3 has no dance partner. Okay. V3 is a little lonely. Right? Does that make sense?
Yes, sir.
Now, Skylar and Rex, what kind of maybe mathematical principle did you guys use to figure that out?
Which is similar.
Yeah, which ones are equal?
That's what I use.
It might begin with an S. Now I'm kind of being a little too leading here. If I draw a line right here, we have what, Jose? Symmetry. That's a line of symmetry, right? If I drew these correctly, put these in exactly the same locations on this trajectory, which looks like a parabola, right? If I fold this over 4, 2, 5, 1, and 6, and 0, they're at the same exact spots, right?
Yeah.
That symmetry only occurs when we ignore air resistance. Okay? This symmetry will occur when we're shooting things short distances, when projectiles are going to close targets. Okay? When we start thinking about baseball games or golf, or if you start thinking about guys kicking footballs and stuff, we lose that symmetry. Okay? We start out having a trajectory that looks like the first half, but the second half drops a lot quicker because of gravity doesn't change. Air resistance. As the ball is exposed to air resistance for a longer period of time, it starts to decrease the horizontal velocity, which makes this resultant steeper downward. Okay, that's right.
Oh, would you shoot 1 million?
We might. In the past, we did that during the fall, which a little bit of getting wet wasn't as bad. But right now it's like 0 degrees outside. A little bit of getting wet is not as comfortable. And water balloons might freeze if we're outside for too long, and that'd be
Do you think
painful.
about this stuff during
So-
football? Really too fun.
Yeah, I do.
Is that how you coach Alex? Like,
Kick it this way a little bit.
No, I don't coach kickers.
Well,
I can't kick. I can just tell him what he needs to do after the fact. I can't get the ball to kick
is
right.
that what you do?
No.
Tell me.
That's how I make sure I can punt the ball straight up in the air, though. Make sure when the ball hits my foot, it's applying an upward force. That's that force directly upward. Okay. All right. Any questions about this? Any questions? Anybody? No, we can't. All right. Does this make sense? And this is all because of
Physics.
symmetry. Okay. Now, let's think about times here for a moment. Okay. If I look at the path of the red, the red trajectory or the burgundy trajectory, either one, they're both symmetrical. Okay. If I look at the red trajectory or the burgundy trajectory, there's another part of symmetry here or another little caveat that's helped by symmetry. Okay. And that is the time it takes to go from 0 to 6. Okay. The time it takes to go from 0 to 6. What do you think that symmetry does to the time? Cuts in half, right? The symmetry cuts that time in half, right? So that means the time it takes for the object, any projectile in this case when there's no air resistance, the time it takes for the projectile to go from its starting spot to its, what's 3? The what? The highest point, good. The time it takes to go from the starting point to the highest point is what in terms of time? Half. Okay? So the maximum height occurs at half the total time. Okay? Definitely a big point. Katrina, stop talking to Kyle.
Sorry.
She's not talking to you, she's talking to you, mommy.
Okay.
No, I was talking to Kyle.
Excuse me.
Last night was pizza.
Thank you. So, the maximum height occurs at half the total time. Or you could say this, you could say T max height
That's confusing.
equals half T total. Okay, could say that too.
Would you have wrote it like that?
I think more mathematically, so I would think this. Okay, those that think more Englishly would think that.
Yeah.
Either way. Okay. All right, now let's look at the x direction. Once again, let's think about these velocities. Which velocity is the biggest in the x direction? Which one? They're all the same. You sure?
Yeah.
Isn't this accelerating?
Downward.
Downward. Does the downward acceleration affect the horizontal velocity? No, it does not. We learned that on Friday with the shot ball and the drop ball, right? Okay.
No, Thursday.
Thursday, thank you. So we know in the x direction, even with directions, okay, V0 equals V1 equals V2 equals V3, which equals V4, which equals V5, which equals V6, which equals,
V7.
if we kept going.
Which equals V8.
Well, we might hit the ground by the time we get to V8. Okay. Or we get a lot of vegetables, either one. Okay. Any questions about velocity in the x direction?
Just make a joke.
I did.
But no one got
I'm
it.
glad you got it. Because you're laughing now.
No, I'm laughing because
I got it. It was just extremely unfunny.
I got
What do you
it.
say?
you have a lot of vegetables.
My jokes are hilarious.
Oh, I didn't.
Okay. Don't say it too loudly. You didn't get V8. You might someone hit you in the head. Another joke. All right. VY.
No, that
Guys, in the y direction, let's think about directions. Okay? Up is going to be what? I know Nan's not here to tell us this, but up is positive, down is negative.
We missed
So
that.
if up is positive, right? If up is positive, then let's rank the velocities. Which one has the greatest velocity? If up is positive.
3. Wait, no.
0, right? This is just for the y direction. So V0 is bigger than V1,
Which is bigger than V2.
which is bigger than V2,
Which is bigger than V2.
which is bigger than V3.
Mr. Brandon.
No, V3 is not smaller than V4. Okay? So it's kind of like the same thing we did up here, right? Kind of like it. That's what we think about directions, right? Because negatives are smaller than positives, right?
Yes.
Now, if we go directionless, we just look at the we just look at the magnitudes. Okay. So if I'm looking at just the magnitudes, I'm looking at the length of my blue vectors, right? Are there any blue vectors that appear to have the same length? Kyle?
V0, V6, I think.
Are those the longest two?
Yep.
Okay. So if we go without direction, we know V0 equals V6, right?
Yep. And then they're greater than
Yeah, they're greater than
V1 and V5.
V1, which equals V5.
Yep.
And they're greater than
V2, which equals V4.
Okay. And they're greater than
V3.
and what does V3 equal?
0.
0. Okay. So now we see a lot of greater than less than signs here. Okay? But the most important part, I would say, is this one right here. The x direction, the velocities do not change because there's no acceleration in the x direction. Okay? Most common misconceptions I see students make, I guess it's not a misconception, it's just a misapplication. Students like to apply 9.8 to the x direction. Don't know why, but they do. Okay? There's no acceleration in the x direction. The only acceleration is in the y direction, which is why we get this. Okay? And symmetry gives us this part, V0 equals V6 and so on. Now, I said there's two most important parts. The first one was that all the x1s are the same. The second most important part is that the V3 has 0 y velocity. Very important. Okay? Because what that gives me, guys, that gives me a way to find where the highest point is. Okay? Because if I know when the y velocity is 0, then I know what time the highest point occurs at. Sorry. Yeah, no, it happens sometimes. If I know when the y velocity is 0, I know where the highest point occurs. Okay? I know the time at which the highest point occurs. And then I can use that to find the actual height. And we'll get to that later on probably this week. Okay? All right. Are there any questions about what we have up here?
Nope.
Okay. A couple more things, and we'll work on an example. All right. This red line, that makes a what? Parabola. Right? Does anybody remember the equation for a parabola?
X squared.
What? My bad. Okay. Does anyone remember the equation for a parabola?
X squared.
Okay, we know it has an x squared, right? Okay. The equation is y equals ax squared plus bx plus c, right? That's the equation for a parabola. Now, earlier this year, we learned a version for one-dimensional kinematics that looked like a parabola. Does anyone remember what that one was?
I don't even remember what one direction is.
Z equals...
6.
Nope.
4.
Nope.
Is it a V
T over
squared?
T.
1/2
What? 6.
a
T.
c
Squared.
plus
Plus
b26 d.
Oh, this is that really.
D naught.
Okay, so d equals 1/2 at squared plus v naught t plus d naught, right? Now remember the naughts mean that it is the initial. Okay. Does that make sense? Not N-A-U-G-H-T. I don't know. No.
Exactly.
Okay, guys. Thank you. Okay. So that's the equation, right? The naughts mean initials. Okay. Now, what do we know about this acceleration? It has to be 9.8. It's constant, right? And for this, it might not be true in the Angry Bird world, but in our world, that acceleration is constantly 9.8. Right? This is a constant acceleration equation. Right? Since it's a constant acceleration equation, right? Should we apply it in one direction or two directions? One. Okay? This is a one-dimensional kinematics equation. So if I'm going to apply it in that one direction, do I need to break my vectors up into their components or leave it as the original? What do you guys think? Components or original? Components. And that's how we spent that time last week learning how to break things up into components. Yes, Rex?
You know how to do that?
How?
Because that would be more complicated.
Well, if we left it in the original?
No.
Keeps going back to Mackenzie every time. Must be on a set cycle. All right. Any questions? Anybody taking pre-calc right now? Kyle? Anthony, you guys know how to do derivatives yet? Derivatives? Okay. Anybody taking calculus right now? Yeah, are you really? No? Okay. If you were taking calculus, you wouldn't know how to do a derivative. Now, a derivative looks at the change in one function with respect to another variable. In this equation, our two variables are time and position. Remember we made position versus time graphs? Right? This was a curved line, right? Because we had an acceleration. And then the velocity versus time graph was a straight line, and the acceleration versus time graph was a horizontal line. Those are all derivatives. So when I take the derivative of this, when I look at the change in this function, we're going to get a linear equation. Okay? So when I look at the change in position over the change in time. Okay? Change in position with respect to the change in time. When I take the derivative, what you do is you take this exponent and you multiply it by what's in front, and then you drop the exponent down 1. All right? So if it's 2, if I take that down 1 value, what's it going to be? 1. And we do 2 times 1/2, which is 2 times 1/2, which is 1. Thank you. Wow, that was surprising. So we know acceleration times time. 2 times 1/2 gives me 1. I leave my exponent as 1. What's my exponent here? 1. So 1 times what's in front. 1 times what's in front of the v. That's just 1, right? 1 minus 0 is 0, right? 1 minus 0 is 0, so that means there's no more t. Because t to the 0 power is 1. D naught, does it have a t? No, so we multiply that by 0 and we get nothing, right? And what we've arrived at then, and this is something I told you earlier about derivatives, okay? The derivative of position is, and remember change in d over change in t, what's that called? Velocity. Is this another equation that we're familiar with?
I'm not familiar with it, but I've seen it before.
Have we seen this before last unit 2?
Yeah.
Yeah. Now these are both one-dimensional kinematic equations, right?
Yeah. Sure. I'll believe you.
Okay. Those are all one-dimensional kinematic equations, right? We will be using them in this unit.
Oh.
Okay. So if I'm going to use these in this unit and they're one-dimensional kinematics, that means I can only apply them in the x and y direction independently. Okay. We can't do x and y at the same time. Can only apply in the x and y direction independently. Because they're one direction, right? Okay. Now, if I look at this equation, there is one component of this that is a scalar, which means it has no direction. Does anyone know which thing in that equation is a scalar? Nope. Everybody think for a second. Now Rex already knocked one down. I'll count to 3 in a second. I want us all to say it. What's the one component, the one variable in those two equations that's a scalar? I mean, it has no direction. Eric, take your earbuds out. Okay? Okay, ready? 1, 2, 3. Time. Good. Time has no vector, right?
Yeah.
Time is directionless. Okay? So that means the time is the same in both equations, in both directions. Okay? And that's the last very important thing for today. Okay? T is the same in the x and y direction. Okay? So what that means, if it takes us 5 seconds to go from 0 and back down to here in the y direction, that's the same amount it takes us to go from 0 to 6 in the x direction. So the time it takes to do this and come back, see I went up to 3 and back, right? That's equal to the time it takes to do this in this picture. Okay? Does that make sense?
No.
Okay. So the time to do this equals the time to do this.
Why? Oh.
Because time is directionless. Okay? All right. Any other questions?
No.